Oh wow! Hi, it's me, Dr. Levine. Today we are continuing our discussion of the second order differential calculus of vector valued functions. We talked all about the first order stuff. We have a velocity vector and a scalar speed, and of course the unit tangent vector, which describes the tangent direction to a curve, sort of irrespective of the kinematics of a particle traveling along that curve. We talked a little bit about the acceleration vector the other day. The goal for today is to continue talking about second order objects, second order stuff with respect to a vector valued function parametrizing a curve in space. And I want to start that conversation by talking about one of the homework problems again that I mentioned in class the other day. So we mentioned this homework problem as being sort of an important model to be able to follow, that this kind of argument is something we're going to do more than once. And indeed we are, and let's do it again. In this homework problem, you may recall, we proved that if I ever have a vector valued function whose magnitude is constant, its derivative is perpendicular to itself. And just to remind you, the argument sort of goes like this. If I have an r whose magnitude is constant, then indeed its magnitude squared is constant, and we can conveniently write that magnitude squared as being the vector dot itself, right? R of t dot r of t. And by using our dot product rule, which says that indeed taking the derivative of a dot product follows the exact same procedure as taking the derivative of a product of functions in single variable calculus, I can imagine that I'm going to find a dot product equal to 0 because I am taking the derivative of a constant squared. So here I'll see that r prime of t dot r plus r of t dot r prime of t is going to be equal to 0, right? The derivative of that constant magnitude must be 0. So what I've shown here is that twice the dot product of r prime with r is 0. So that means, of course, that r prime is perpendicular to r. Now, why this is relevant is because there are lots of vectors that we imagine as being constant in magnitude. There are important unit vectors that we use to describe the geometry of a curve through space, the first of which we introduced just the other day as being the unit tangent vector. So recall, t hat is the velocity vector divided by its magnitude, the speed. And its magnitude is always 1, right? This is the unit tangent vector. So what I better imagine is that I should observe that t hat is perpendicular to t hat prime. So what I would like to explore is, why is it that t hat prime should be perpendicular to t hat, and what direction ought it point in? So if I draw a diagram of my vector valued function in space, there's my curve parametrized through space. I have the position vector there pointing up to the curve. I have the tangent vector, r prime, the velocity vector, which of course I'm interested now in thinking of normalized as t hat. So there's t hat, it has unit 1, it's r prime scaled down by the speed. And now what I'd like to add to the picture is t hat prime, a vector that I know to be perpendicular to t hat, but my question is, perpendicular where? Of course, if I imagine all the vectors perpendicular to t hat, they form a whole plane. That was our definition of the plane, right? Is the set of all points perpendicular to a given vector. But what I'd like to argue to you is that the only evident, the only obvious place to put t hat prime is perpendicular to t hat in the direction into which it's curving. Right? So t hat is tangent to my curve, but t hat will be changing as the curve curves, right, in sort of the direction of curvature. And t hat prime will be a vector that points in that direction of curvature. So I'd like to try to add it to my picture now. There is t hat prime. The calculus suggests that it must be perpendicular to t hat, and the only sensible place for it to point, if it is the derivative of t hat, is the direction in which t hat is changing, this sort of direction of curvature. So I'm going to indicate there that these two vectors are perpendicular. And this actually indicates to us sort of the second important direction associated with the vector valued function at any time. If the most important direction is that tangent direction, tangent to the curve, the second order of importance should be this direction into which I expect the curve to be moving in time. And this is actually exactly how we're going to define the second most important unit vector associated with the curve, which is the normal vector. So let's define now definition. We know it's an important time in this class whenever we write DEF : underline. So definition, the unit normal vector n hat, n for normal, will be t hat prime. But of course, I can't expect t hat prime to be a unit vector. T hat could be changing really quickly. It could be changing really slowly. So the magnitude of that change might not be unit. So I need to normalize this vector. So if I normalize t hat prime, which I know to be orthogonal to t hat, then I will have n hat, which is the unit normal vector, and I will add that to our picture now in red. Why not? So here it is. This is n hat. This is n hat. It is the unit normal vector, and it points orthogonally to t hat. In which of the many directions that are orthogonal to t hat? In the direction of the instantaneous curvature. So let's go ahead and compute n hat for our favorite curve in space, of course, the unit standard helix. So for example, let's find n hat for the helix. R of t equal cos t sine t t. So this helix will spiral up the z-axis. We know that at any point the tangent vector is pointing precisely tangent to the curve, and we would like to identify this normal vector pointing perpendicularly to that tangent direction of motion. So of course, it's worth writing again because we're only just meeting this critter, that n hat is the normalization of t hat prime. So let's go ahead and find t hat. T hat, I know, is r prime normalized. R prime we can find without too much trouble. Sine t, cos t, 1 appear to be the derivatives of all of those component functions. We found the speed of this to be square root of 2 the other day, and that's a valuable number to remember just because we're going to be talking about this particular helix a lot. So the norm of r prime will be square root of sine squared t plus cos squared t plus 1 squared, which looks to be the square root of 1 plus 1, which is indeed square root of 2. So t hat will be minus sine t over square root of 2 cos t over square root of 2, 1 over square root of 2. So now I'd like to invite you to take a minute to pause the video and go ahead and find t hat prime and normalize it. Did you do it? Did you pause the video and do it? Pause the video. Go ahead. Okay. T hat prime will look to be minus cos t over root 2 minus sine t over root 2, comma 0. And if I were to normalize this vector now to get n hat, I'm looking at, is it cos squared over 2 plus sine squared over 2 plus 0? And that looks to be square root of a half. Not a very satisfying answer, because what we're about to see is that n hat t hat prime normalized is, I'm going to take t hat here. Yeah, I'm going to take t hat here, which already is sort of, has the square root of 2 in all those denominators, and I'm going to divide away that 1 over square root of 2, and I'm just going to be left with minus cos t minus sine t, comma 0. So there's our n hat. If we jump into Desmos 3D and plot these vectors together, here in green we see that unit tangent vector t hat. It's always of unit length. It's pointing tangentially to the curve. And there's n hat in red. It is pointing directly in the direction of curvature, so it's sort of indicating the instantaneous direction into which the curve will be curving. And it is pointing directly towards that central axis, that central z-axis. So evidently key in this question is the notion of curvature. We're talking about the direction into which the curve is curving. This is evidently a second order idea. If the first order thinking is a tangent vector and a tangent line, right, the first derivative helps us find the slope of the tangent line in single variable calculus. The second derivative helps us identify the concavity, right? How curvaceous an object is. So a really necessary question for us to ask next is, how do I quantify curvature? So the big question is how to define curvature. So I should draw a picture. Evidently, this is a point here of low curvature. Whereas here I would see a point of really high curvature. So I encourage you, pause the video and go ahead, discuss with yourselves or the voices in your head or whomever might happen to be sitting next to you. How would you define curvature? How would you geometrically identify this point here in blue as being a place of low curvature, whereas the place in pink as being a point of high curvature? Did you do it? Did you pause the video? I have no way of knowing. So one answer would be to ask, how quickly does the tangent direction change? So for instance, here at the point of low curvature, I can see that t hat does not change very much over some small sort of segment of arc. Whereas here at the point of high curvature, sort of, if I imagine that right here I was trying to sketch out 1 centimeter of arc and ask how much did t hat change, over that same centimeter of arc down here, t hat changed a lot. So I traveled the same sort of arc distance, but t hat changed greatly. So the answer we might give is curvature is how quickly t hat changes direction. So I'm talking about some derivative of t hat. How quickly does t hat change? But the derivative I want to ask about is not with respect to time, right? Remember, part of the conversation we're having is how do I divorce the kinematic picture of a particle moving along a curve, perhaps really quickly, perhaps really slowly, perhaps at variable speed, perhaps speeding up, perhaps slowing down. How do I divorce that kinematic story from the geometrical story of the curve? And the curvature better be a geometrical quantity and not a kinematic quantity. So I want to take a derivative of t hat, but not with respect to time. The way I should define the curvature is how quickly t hat changes with respect to arc, with respect to the arc length. And that's exactly how we define it. So here's another definition. Again, big drum roll moment. I'm writing DEF, underline, colon. So it must be important. Definition, the curvature, which we give the symbol kappa, is defined to be the derivative of t hat with respect to arc length. If t hat changes greatly over a small amount of arc, it's because there's high curvature. If t hat changes very little over a small amount of arc, there must be low curvature. But of course, this is a vector, and I want a scalar to represent the curvature, so let's take the magnitude. This is the definition of curvature. The magnitude of dt hat ds, where s is arc length. Now, the conceit here is that you will never have t hat as a function of arc length. So this is a lovely definition. Theoretically, geometrically, practically, it is not very helpful. So what we better do is use the chain rule so that I can actually come up with a formula that's usable for us. So the chain rule, so via chain rule, I'll write a better definition of curvature for computational purposes, which is to say that kappa, which is dt hat ds, is equal to dt hat dt over ds dt. Sorry. A good way to remember chain rule is whenever derivatives behave like fractions. Right? Derivatives are not fractions, but sometimes they behave like fractions. And in some shorthand way, whenever a derivative behaves like a fraction, it's because you're invoking the chain rule. So it's as if the over dt's cancel. And of course, what I see here are two functions that I do have my hands on pretty readily. Of course, dt hat dt is just t hat prime. And ds dt, which was already a scalar, actually. Can we call that out? My bad. Strike one. ds dt was already a scalar. I didn't need to put magnitude there. ds dt is just the speed. It's arc length per unit time. It's the magnitude of r prime. So this is the curvature. It's t hat prime divided by the speed. Why? Because that's a surrogate for dt hat ds. rate of change of the tangent direction over a piece of arc. Okay, let's go ahead and compute the curvature for the unit helix. So let's find the curvature of our unit helix, r of t equals cos t sine t, comma t. This, of course, is the example we will be working with throughout the entire duration of this unit, and we've already done the vast majority of the work to compute this already. So kappa will be t hat prime in magnitude divided by the speed in magnitude. And of course, I am intentionally switching between ds dt and magnitude of r prime for speed because those are synonyms, and we need to be really comfortable seeing those as synonyms. So I have both of these already computed just a little north in the OneNote. So let's go see. Here's t hat prime. Here's t hat prime in magnitude. It was square root of 1 over 2. Square root of a half. So t hat prime in magnitude was 1 over square root of 2. ds dt was the speed. The speed, of course, we know was square root of 2. So what do I have? I have 1 over square root of 2 divided by square root of 2. Of course, remember, dividing by square root of 2 means multiplying by the reciprocal, square root of 2. So it looks like the curvature of this helix is 1/2. So 1/2 is a number that is summarizing how curvaceous the helix is that at that time. Okay. So we're thinking of curvature as being some measure of the curviness of a shape at some point, which of course feels like a direct correlate. It feels like a direct parallel to the idea of concavity from single variable calculus. Of course, concavity, we know, is intimately related with the second derivative. So a really important question should be, how does acceleration, right, r double prime, the second derivative vector function, how does the acceleration vector cause curvature? If curvature means some flavor of concavity, how is the acceleration vector related to that curvature? And I want to break down how there's something fundamentally different than the second derivative in single variable calculus, which is that my first derivative, the velocity vector, is built out of two things. It's a vector, meaning it has both magnitude and direction. So recall, my velocity vector, r prime of t, is a vector that has both magnitude and direction. The magnitude is ds dt. The direction is t hat. So the magnitude of the vector is the speed. It's the magnitude. And t hat is the direction. And if acceleration is the rate of change of your velocity, then acceleration can cause your velocity to change in two ways. It can cause the magnitude of your velocity to change. It can cause you to speed up. Or it can cause the direction of your velocity to change. It can cause you to curve. And of course, we already know this, because if I were to say, here is the sun, and this was you, and you were traveling towards the sun, we know that the acceleration vector due to gravity is always pointing radially back towards the sun. And if you were already traveling in this direction, the acceleration due to gravity would only cause you to hurtle faster and faster into the sun. This got dark really quick. I'm sorry. So all that would happen in this case is that you would hurtle into the sun faster and faster. However, in another scenario, if I were to draw the sun and I were to draw you, oh, how about this? I'll draw the Earth. So here's the Earth. Of course, the Earth isn't headed directly towards the sun. The Earth is always moving sort of tangentially. Then we know that when the Earth is sort of moving perpendicularly to this acceleration vector, what results is a circular orbit. So acceleration breaks down in two ways. When acceleration is parallel to the tangential motion, it just causes you to get faster and faster and hurtle into the sun. And when acceleration is normal to the direction of motion, it causes you to curve. It causes you to move circularly around the sun. And these are, in fact, quite precisely the exact two operations, the exact two functions of acceleration. They cause you to do one of two things, or both simultaneously. Get faster and faster, or to change your direction. And we can observe this precisely by making use of this perspective on velocity. That velocity is built out of two things, magnitude and direction, speed and t hat. So, if I observe that my acceleration vector is precisely the derivative with respect to time of r prime. The acceleration vector is just r double prime, the derivative of r prime. Then it's the derivative of a product of two things. It's the derivative of my speed, ds dt, times t hat. And of course, I can use the product rule. And I see that I have the derivative of the first thing, leaving the second thing alone. So d squared s dt squared t hat. Of course, this is a cumbersome piece of Leibniz notation, but all this means is the linear acceleration. Sort of how much I'm speeding up. How much is my speed increasing? The rate at which my speed increases, my linear acceleration, or my scalar acceleration. Plus product rule. I'm just going to do product rule, which says leave the first thing alone, take the derivative of the second thing. And what, of course, is t hat prime? It's something that points in the normal direction. So let's quickly recall that n hat is t hat prime but normalized. So what is t hat prime but n hat times the magnitude of t hat prime? But t hat prime appears in the definition of curvature, which is exactly what I expect. I expect this second piece of the acceleration vector to be telling me about curvature. So what is it again? It is that curvature equals the magnitude of t hat prime over ds dt. So t hat prime in magnitude is speed times curvature. So if I plop this in above, I get that t hat prime equals ds dt times the curvature, n hat. All of this now I substitute in for t hat. And what I find is that the acceleration vector is built out of two pieces. The linear acceleration, the second derivative of arc length, right, the derivative of the speed, the rate of change of your speed, times t hat, plus speed squared times curvature times n hat. Acceleration does two things. When acceleration points in the direction you're traveling, it causes you to speed up. If you're traveling towards the sun, you are going to hurtle faster and faster into the sun. The second thing it can do is if acceleration points normally to your direction of travel, it will cause you to curve. If I am moving normally to the direction of the sun's gravitational pull, I will move in a circular orbit, as does our planet, around the sun. We call this the tangent normal decomposition of acceleration. The acceleration vector has two components. It has a component in the tangent direction and a component in the normal direction, where the tangential component, as one expects, just causes you to speed up. And the normal component causes you to curve. Let's put this in a picture. At this point, I have two important vectors. I have t hat, indicating my tangential direction of travel, and I have n hat, indicating my normal direction of travel. Or sorry, I should say n hat is the direction perpendicular to the tangent direction, and it indicates the direction into which I will be curving. R prime, and there's R prime, it's the velocity vector, it's the not normalized yet version of t hat. And here is where we put the acceleration vector in our picture. The acceleration vector, A, which is R double prime, lives somewhere in the plane spanned by t and n. And I can project it back onto the n hat axis. I can project it back onto the t hat axis. And this projection in the t hat direction, that's what I call a sub t. It tells me how fast I'm speeding up. The more well-aligned your acceleration vector is with your direction of travel, the more quickly you'll be speeding up. The component that lies in the n hat direction I call a sub n, and it is the normal component of acceleration. The more well-aligned a is with the normal direction, the less investment acceleration is making in causing you to speed up, and the more investment it is making in causing you to curve, in causing you to change direction. The last thing let's do then together is to return to our helix and find these tangential and normal components of the acceleration for the helix. It'll be easy, because we know a lot about this helix already. We know so much. We know that ds dt for the helix, this is the magnitude of the acceleration vector, the speed of the helix was constant and equal to square root of 2. We also know that the curvature we computed earlier was equal to 1/2. So putting together these normal components should be pretty straightforward. I should find that the acceleration vector a sub t t hat plus a sub n n hat has components a sub t equal the derivative of the speed. Right, let me write it this way. I know that this d squared s dt squared is cumbersome Leibniz notation. All that it means is I am differentiating again the speed, but this particle has constant speed. A particle traveling along this helix with this parametrization has constant speed. I'm taking the derivative with respect to time of square root of 2, which indeed is 0. So this normal vector is pointing only, or sorry, I should say this acceleration vector has no tangential component. It's pointing only along n hat. And let's see what happens to a sub n. A sub n, so ds squared, ds dt squared kappa, is going to be, the speed was square root of 2 squared. The curvature was 1/2. 2 times 1/2 is 1. So in this particular case, a was equal to 0 t hat plus 1 n hat. Let's see if we agree with that. We computed n hat not too long ago. It actually was kind of long ago. Here was n hat. N hat was minus cos t minus sine t, 0. So from above, we found that n hat was minus cos t minus sine t, 0. The question is, do we agree that this is equal to r double prime of t? I think so. If I take 2 derivatives here, twice the derivative of cosine is minus sine, then minus cosine. Twice the derivative of sine is cosine, then minus sine. Twice the derivative of t is 0. So indeed, our tangent normal decomposition reveals that in this case, because I had a parametrization with constant speed, n hat was r double prime itself. Okay, that's it. Thank you so much for joining me and following along with this video lecture. I apologize that I couldn't be there in person. This is one of my absolute favorite lessons to give. I love seeing how all of this second order stuff sort of plays out in this new context, retelling the story of single variable calculus here in 3 dimensions. It's really fun, and it's a real pleasure to sort of see those ideas that we've spent so much time developing manifest themselves in this 3-dimensional context. Look forward to next week, where we will add one final vector to the picture. From t hat to n hat, we will add one third vector to complete the 3 vectors necessary to describe a full 3-dimensional picture of the kinematics of a curve. But I will see you then.